Hello again, everybody. I'm going to do a few more Van de Graaff generator demonstrations, but I want to redo the hair charging experiment or demonstration. I remembered that I had a wig in the storeroom, and sometimes this works and sometimes it doesn't, to show the electric field lines with my hair. So we'll do that again before I go on to the new information. Just a couple more things about the Van de Graaff. The other thing that I forgot to mention in the last video is that I was standing up high on a milk crate because I wanted to be isolated from the ground. If I have my hand on this Van de Graaff and I'm standing on the ground, the charge is just going to go through my body into the ground and I'll never build any charge up. So I want to be isolated from the ground, and that will allow the charge to build up and not leak away. So let's give it a shot and see if my hair stands up now. Okay, so here we go. I feel a little something. I think I see something reflecting in the Van de Graaff. Loosening it up, and again the hair is hopefully aligning with the electric field lines, so my head is now a nice spherical conductor demonstrating electric field. Alright, I don't know if it'll go anymore, but hopefully you see a nice little display of my hair. The other thing I want to point out is something else we're going to see in this video. Watch what happens when I stick my finger out. And you might even be able to hear the hissing out of my fingertip. And I make a blunt fist and it stops. Alright, so this seems to leak the charge away. Okay. Alright, so let's move on. Let me step off, discharge, shut off the Van de Graaff, discharge it, and then actually, do I want to zoom? Yeah, I could zoom in now a little bit. Alright, that looks about right. Okay. All right, so there we are. Now, another demonstration I want to do, just a couple quick things. Pie plates. All right, metal, aluminum pie plates. I'll turn on the Van de Graaff generator. Spooky, haunted, right? And obviously, we know what happened. Hopefully you know what happened. This Van de Graaff became negative. Some of the negative went into the pie plates, and then negative repel, and it lifts off the Van de Graaff generator. And here's a fascinating thing, something we really haven't talked too much about, is the strength of this electrostatic force. Because this pie plate is pulled down through the force of gravity by an object. Planet Earth, the entire planet Earth, pulls down on this pie plate and holds it to the top of this Van de Graaff. All of Earth. Every mountain, the Mount Everest, the Indian Ocean, Australia, Europe, all the lava inside the molten core of the Earth, all that mass pulls down on this pie plate and fixes it with the force of gravity. Aligned against that, I've got one dinky Van de Graaff generator, even made of plastic and a little rubber and a thin metal. If I whack this, I could dent it. So it's not that robust at all. And yet, one Van de Graaff generator against the whole Earth, and the Van de Graaff generator easily wins. And the reason why it easily wins is because it is acting through this electromagnetic force. Far more powerful than gravity. I'm not talking millions, not even billions, not even trillions. There isn't even a word for how many more times powerful mass versus charge, the electromagnetic forces compared to gravity. All right, so, but let's move on to another quick little demonstration. This one's really fun. So these pie plates, they're pretty light, but they have a significant amount of mass compared to this. A sharp little thumbtack of no mass. Okay. So, ready? Nothing. And it's a little like my finger when I was standing and I put my finger out and it was discharging. Let me just show you that I didn't secretly, like a magician, flip something on the Van de Graaff and shut it off. I put this discharge sphere here, and now all I'm going to do is take this wooden meter stick and knock the the thumbtack off. Sparks return. So the sharp point eliminated the sparks. Pretty interesting. And another thing, before I put the Van de Graaff generator away, is the spacing also I'm going to talk about. Watch when I increase the spacing. See, it takes much longer for the sparks to occur. But if I decrease the spacing, people say, oh, it's because it's got less distance to go. Well, not really. It's something to do with the equations that we learned. Why does the spark happen earlier when the distance is smaller? Like, for example, this has charge on it. Spark can't happen. But I decrease, and then boom, if I get small enough. So why is that happening? So these are the things that we're going to discuss in this little Van de Graaff generator video. Okay, so the first thing, why does the decreased gap cause the lightning to occur, the spark? So, topic for today, we've got a charged cloud. It has a certain voltage difference between the ground, the earth, and the cloud. Over here, when the cloud is above a field, we've got a pretty large distance, comparatively speaking, from the cloud to the ground. So the basic idea of voltage is it's electric field integrated over path. But in this case, we're just going to keep it real simple and just do the simple if we had a constant electric field ED. It's more complicated, but this will be enough to get us the main concept why the lightning happens when the gap decreases. So big distance, small electric field to get that same voltage. When the cloud finds itself over a mountain or a tree or a church steeple or something like that, that rises up, we have the same voltage, but now with a diminished distance, the electric field has to be larger to create that same voltage. So the electric field becomes large when the gap becomes small, and that then makes the spark occur, because then it gets beyond the point where air can hold itself together, ionized spark. Okay? So that's why lightning strikes tall points. Diminished distance, increased electric field. Okay? So the other thing, the thumbtack, why did that cause the spark not to occur? So the other thing that happens when you have an irregularly shaped metal like the thumbtack is that the charge is no longer going to be uniform as if it were a nice, perfect sphere. What happens is, because the electrons tend to repel themselves, this electron is repelled by these two, but at a sharp point, there's nothing on this side repelling the electrons away from that sharp point, whereas these are kind of repelling more or less more lined up than over here. So over here, the electrons back here all tend to force and concentrate charge at that sharp point, which causes a discharge. Why? Why is there an early discharge at sharp points? Well, here's our basic formula for electric field. Again, we're just simplifying to get the idea of why that happens. And since the charge accumulates here, we've got more Q packed in to that one little space. And we also have a smaller radius of curvature here than we have here. So both those effects magnify the electric field beyond 3 × 10⁶ And at that thumbtack were tiny little lightning strikes happening very early. As soon as I flip the switch, there's lightning, and the Van de Graaff is losing charge right away. So that's, for a nice Van de Graaff to work big sparks, you need it to be smooth so that it builds up enough, a lot of charge, and boom, okay? Another thing that you might have to do with conductors is possibly calculate the charge density versus electric field relationship at a surface. So by the way, if you didn't copy that down yet, let me create a little pause. All right, so what I'm going to do is I'm going to use Gauss's law, but I need to imagine the right kind of Gaussian shape. So my Gaussian shape will be like this. It could be a box or it could be a cylinder, it doesn't matter. Some of it is inside the conductor and some is on the outside, so it kind of cuts off a portion of the surface. And Gauss's law for this surface then now, if we think about all the things we know about a conductor, the electric field only exists at the surface and it points directly away from the surface. That means there's no flux on this part of the surface, none here, none here, none here, and none here. There's only flux along that top surface where the electric, well, it's going to be coming in this case, with a conductor negatively charged. So, right here, that's where the flux occurs. So we could write E at the top times that Gaussian area equals Q enclosed over epsilon 0. Now, what's the Q enclosed? Well, if you look here, the Q enclosed is right here on this diagram. The amount of the conductor surface that's cut off by our Gaussian surface. Remember, there's no excess charge anywhere inside. It only resides on the surface of any conductor in static equilibrium. So, that charge will be sigma times area, cross-sectional area of our Gaussian surface, all over epsilon 0. And we have a very simple relationship between the electric field at the surface of the conductor and the charge density of the surface of the conductor. So there it is. All right, so that's pretty much rounds out all the stuff that we could learn from a Van de Graaff. Well, there's more, but in terms of how it relates to the AP Electricity and Magnetism curriculum. So I hope you enjoyed our little demonstrations, charging up with the hair standing on end, the thumbtack not flying off, and I'll see you in the next physics video next time with something we call capacitors.